In this video lecture, I'm going to continue our discussion of isomers. Remember, an isomer, they're compounds that have the same formula but different structures. In previous lessons, we discussed structural isomers, specifically coordination isomers and linkage isomers. And I know in structural isomers, atoms have different connectivities. That means you have different metal to donor atom bonds of some sort. We talked also about stereoisomers. So same chemical formula, same connectivities, so same bonds, but different spatial arrangements. We looked specifically at cis-trans and FASMer. In this lecture, we're going to define and discuss optical isomers. So the definition of an optical isomer, compounds that are non-superimposable mirror images of each other. And we'll look at some examples. So optical isomers are stereoisomers. So a stereoisomer, remember, the same chemical bonds but different spatial arrangements. And we saw our geometric isomers were cis-trans FASMer, so different bond angles. Specifically, optical isomers means we have non-superimposable mirror images of each other. So an example here, we have an octahedral complex with 3 bidentate ligands. So each of these represents a different bidentate ligand, specifically ethylene diamine. So I have one ethylene diamine here, another ethylene diamine there, and another ethylene diamine there. If we create the mirror image, so hold that up in a mirror plane, and then try to superimpose the 2 molecules on each other, there's no way to get them to completely superimpose on top of each other, which means they are different structures. And you can see the chemical formula up here, COEN3. So tris ethylene diamine cobalt 3. There are 3 different types of optical isomers that I want you to remember. And they are just the most common structures that we see in our textbook in this chapter. So the first is if you have a tetrahedral arrangement with 4 different ligands. The second, as we see in this slide, an octahedral structure with 3 bidentate ligands. And the third, you have an octahedral structure with 2 bidentate ligands. But what's very important, they must be in the cis position. So remember, if I have an octahedral structure with 2 of the same ligands, so in this case 2 bidentate, maybe 2 ethylene diamine, 2 oxalato, they must be in the cis position, or that means in adjacent positions. And we're going to go ahead and look at some examples here, and there'll be other videos that you'll watch where you're going to actually see models that are made and rotated. But again, for our class, what I want you to really remember, optical isomers, these 3 examples. So here are some definitions. So stereoisomers, specifically optical isomers. So optical isomer or enantiomer, those are synonyms of each other. So remember the definition of optical isomer, stereoisomers that are non-superimposable mirror images. So we saw this is an example of an octahedral structure with 3 bidentate ligands. Your hands are a great example of optical isomers. So if you hold your left hand up and your right hand facing it, you see that they're mirror images of each other. But if you try to superimpose your hands, there's no way, because if you have both of your palms up, then your palms match, but your thumbs are on the opposite side. If you rotate it around, then your palms no longer match. And I'll have a video where you can see that more clearly. And here is another example. And I can see in this case, the mirror plane is represented with this dashed line down the center. So this is how we represent when we're sketching a mirror plane. And then I can see I have my metal center, cobalt in the center, on both of them. And then the mirror plane, whatever is sticking pointed towards the mirror plane. So those are the mirror images of each other. And I can see these chloros are the mirror images of each other. And then I have two ethylene diamines. So I can see this one nitrogen is pointing down, so those are the mirror images, and then to the outside of that mirror plane. And lastly, one nitrogen pointing up of ethylene diamine, and then towards the out and back in. So these are mirror images, and if you make a structure of these, you'll see that they are non-superimposable, which means they are optical isomers. And another definition, a molecule or ion that exists as a pair of enantiomers is said to be chiral. So you would say this molecule is chiral. Its mirror image is also chiral. These are a pair of enantiomers, or these are optical isomers of each other. So lots of new definitions there. Let's look at one other example. I mentioned if I have a tetrahedral structure with 4 different ligands, we have another molecule that has an optical isomer, or we can say that it's chiral. So our example with tetrahedral, let's maybe call it zinc, chloro, bromo, aqua, and amine. So I know this is a tetrahedral structure. I know I've got a coordination number of 4 because I've got 4 ligand, 4 donor atoms. I know because chloro and bromo are each -1, water and amine are neutral, zinc is +2, and zinc 2+, if you look at your periodic table, count across 12 minus 2 is D10, so that tells us we have a tetrahedral arrangement. So to draw this, zinc in the center, and our tetrahedral structure, again showing that 109.5 degree bond angle, wedge for coming out of the plane, dash going back into. And now I can attach my ligands. So I've got anywhere I want right now, chloro, bromo, aqua, and amine. And my goal is to show that we have optical isomers. So I'm going to draw the dashed line, again to represent the mirror plane. And now I need to draw the mirror image. So whatever is going towards the mirror image, that line will be straight up, and then I can see my other straight line is going away from the mirror plane. And then my wedge and my dash. So you need to practice drawing these. And now I can see straight up, I've got NH3. In the dash towards the mirror plane, I've got my Cl, the wedge, Br, and out, H2O. So those are examples of a tetrahedral structure with 4 different ligands. And if we make this, and we'll watch a video where these are made for you and you can see how when you try to superimpose them, they are non-superimposable. Mirror images, which makes the molecule chiral. And we can say that these 2 structures are enantiomers of each other. We also say they're optical isomers. Now let's look at the next practice exercise. So in practice exercise 2 in this chapter, it says, do either cis or trans, and we could name this, we have chloro and ethylene diamine. So dichloro bis ethylene diamine, cobalt, the charge of the cobalt would be +3. Cobalt 3 have optical isomers. And the answer is yes. So in the start of this lecture, we said optical isomers exist if you have an octahedral structure, 2 bidentate ligands, in the cis position only. So let's draw those. So I have my cobalt center, octahedral structure. And I know I have to have a cis position, so I will draw one ethylene diamine here. And when you're drawing a bidentate ligand, you always need to have the bidentate ligand connected on adjacent positions. I could not make an ethylene diamine at 180 degrees because that is too large of a bond angle. The molecule or the ligand is too small. So that is not possible. Let's draw another ethylene diamine, so cis. So this other ethylene diamine I could put right here, which would be cis to this, or right here. So that would be another ethylene diamine. It's really important that you connect the two donor atoms. So ethylene diamine, remember, is NH2, CH2, CH2, NH2. I'm emphasizing just my donor atoms of the N for simplicity. And then I have two Cls as my other ligands. Now let's draw the mirror plane so we can draw the optical isomer. Again, cobalt in the center, line, line, wedge, wedge, dash, dash. This time I'll start with my chloros, so one straight up and one away from the mirror plane. I'll now draw the next ethylene diamine. This represents the mirror image of these two. And my last ethylene diamine, down and away. And so we could say that these two are optical isomers of each other. And to be correct, let's go ahead and add my charge of +1 on this complex. So again, we know that they're optical isomers because we remember octahedral with two bidentate ligands in the cis position. We do indeed have optical isomers, and there'll be other videos for you to watch so you can see these models as well made. The last slide for this topic, looking at some more definitions. So enantiomers, remember enantiomers, these are the same as optical isomers, those are synonyms. So the physical properties of chiral molecules are the same except in the instances where the spatial placement of the atoms matters. So one good example is the interaction of a chiral molecule. So a chiral means it has an optical isomer or it has an enantiomer, is with plain polarized light. So we have a white light source, so no polarization, going through a polarizing filter. So we get polarized light traveling in only one direction. And you travel this through an optically active solution. So a solution is optically active if it contains a molecule that is chiral. And there is some type of an analyzer that measures the rotation of plane polarized light. And so you know the direction that the plane polarized light entered the sample. So you can measure the direction at which it's coming out of the sample, and the instrument would show you that it has rotated. So if one enantiomer of a chiral compound is placed in a polarimeter, and a polarimeter would be an example of an instrument that would measure this for you, and plane polarized light is shown through it, the plane of polarization, light will rotate. If one enantiomer rotates light 32 degrees to the right, the other will rotate 32 degrees left. So if you had a solution that had only one of the two enantiomers, if one enantiomer rotates light, let's say 15 degrees to the left, the other enantiomer would rotate light 15 degrees to the right. So that's why we call these optical isomers, because that chiral molecule rotates plane polarized light.